Hey everyone, and welcome. Today we're going to talk about a secret weapon, a powerful mental tool that physicists use to figure out how the universe works. And a lot of the time, they don't even need a calculator.
So let's put you in the driver's seat. Imagine you're a mission planner over at NASA. Your job? Get astronauts to Mars. Sounds simple, right? Wrong. It's an insanely complex problem. You've got to worry about fuel, oxygen, how long the trip's going to take, and all that nasty cosmic radiation bombarding the crew the whole way. We're talking millions upon millions of kilometers.
So, with all that going on, where do you even start? How do you pick the best plan? Well, you can't just throw a dart at a board, right? What engineers do is they compare a bunch of different plans. We'll call them Mission A, Mission B, whatever, so they can really understand the trade-offs. What do you gain and what do you lose with each choice?
The secret is to start by simplifying things a lot. So for our little thought experiment here, we're going to assume our spaceship is flying in a perfectly straight line, it's starting from a dead stop, and it has a nice, steady, constant acceleration. And you'll see, by boiling it all down to just these basics, we can actually uncover some really deep truths about how physics works.
All right, let's get into it. Here's our first challenge. We're going to set up 2 mission plans and watch what happens when we change just one little thing. You'll see how that one change sends ripples through everything else.
Okay, so here's the setup. On one side, we have Mission A. This is our baseline, our control group, you could say. It goes a certain distance in a certain amount of time. Pretty straightforward. But then you've got Mission B over here. This is the express route. The goal is the same, travel the exact same distance. But get this, we want to do it in half the time.
Now, common sense tells you we're going to have to go faster, right? No brainer. But the real question is, how much faster? So what do you think? Take a guess. Do we need to go a little bit faster, a lot faster, or is there maybe some exact predictable relationship here?
Okay, so there are 2 ways we can figure this out. We can do it the textbook way, busting out the paper and pencil and grinding through the algebra, or we can use the physicist's shortcut. Let's actually look at both, and we'll start with the long way, just to appreciate how cool the shortcut is.
All right, deep breath, let's muscle through the math. First, we start with that basic formula you probably remember, average velocity equals distance over time. Now, to compare our 2 missions, the easiest way is to set up a ratio, the velocity of B divided by the velocity of A. Then we just plug in the formulas for each. And here's the key. Since the distance is the same for both missions, it just, poof, it cancels out. That leaves us with a super simple ratio of the times. We plug in the fact that time B is half of time A, and boom, we've got our answer.
And what's the answer after all that work? It's 2. A perfect, clean 2x. To go the same distance in half the time, you need to have exactly double the average velocity. It's a really neat result for sure, but man, there was a much faster way to get here.
But hang on, think about it. Do we really need to write all that out, do all those steps? The answer is a big fat no. And this right here is where the magic really starts.
It all comes down to a concept called inverse proportionality. Just look at the formula again. Velocity is distance divided by time. If we hold the distance constant, then velocity is what we call proportional to 1 over time. That's the fancy way of saying they have this perfect inverse dance. Whatever you do to the time, you do the exact opposite or reciprocal to the velocity. So if you slice the time in half, you multiply the velocity by 2, the reciprocal of 1/2. Same answer. Instantly. No algebra needed.
Okay, that was a pretty cool warm-up, right? But what about something a little trickier? I mean, velocity is one thing, but you don't just magically have velocity. You have to accelerate to get there. So let's up the stakes a bit.
So back to Mission B. If we're serious about getting there in half the time, what does that do to the acceleration we need? How much harder do the engines have to push? Let's use our brand new shortcut and see if we can figure it out.
Well, get ready because this relationship is even more dramatic. It turns out that for this kind of motion, acceleration is proportional to 1 over the time squared. So it's not just an inverse relationship, it's an inverse square relationship. That squared part is a huge deal. It means whatever factor we change the time by, the acceleration changes by the reciprocal of the square of that factor.
So let's just follow the rule. We cut the time in half, right? So the factor is 1/2. The reciprocal of that is 2. But now we have to square it. 2 squared is 4. You heard that right? To get there in half the time, we need a mind-boggling 4 times the acceleration. Now that is a much, much bigger price to pay than just doubling your speed.
And this is exactly why this shortcut is so powerful. It's not just a party trick. Let's say our baseline acceleration, Mission A, was a comfy 10 meters per second squared. That's about the same as gravity here on Earth. Well, 4 times that is 40. That's a bone-crushing amount of G-force. No human crew could handle that for a long trip. So just like that, without plugging in a single big number, we just proved that Mission B is a total no-go. It's off the table.
So let's just recap what we figured out. We've got 2 different relationships here. For velocity, it's a simple inverse relationship with time. You have the time, you gotta double the velocity. Simple. But for acceleration, it's an inverse square relationship. You have the time, you have to quadruple the acceleration. It's seeing these fundamental patterns that's the real key here.
All right, you ready for one last puzzle? Let's totally flip the script. Everything we've seen so far has been an inverse relationship. One thing goes up, the other goes down. Now let's see what happens with a direct relationship.
Okay, introducing Mission C. For this one, we're going to stick with the same comfortable acceleration we had in Mission A, but we're going to let the engines burn for 50% more time, so our time factor is 1.5. The big question is, with that extra time, how much farther does our ship actually go?
Well, if we look back at our physics toolkit, those motion equations tell us something really interesting. When acceleration is constant, the distance you travel is directly proportional to the square of the time. See? No 1 over this time. It's direct. So whatever we do to the time, we do the square of that to the distance. So our time factor was 1.5, right? Let's square that. 1.5 times 1.5 is 2.25. Now just stop and think about that for a second. By adding just 50% more time to our trip, our spaceship travels more than double the distance. That is a fantastic trade-off. You get way more bang for your buck, so to speak.
So, after running through all these missions, what's the big takeaway? What have we really learned here? Well, it's more than just the trick for solving homework problems. We've basically unlocked a whole new way of looking at the world, one that's focused on the relationships between things, not just the numbers themselves.
This way of thinking, proportional reasoning, it lets you see almost instantly how tweaking one thing is going to affect everything else. And the most amazing part? You don't even need to know the exact distance in kilometers or the time in seconds. All you need is the factor of change. Are you doubling it? Having it? And this way of thinking isn't just for spaceships. It works everywhere in physics, from gravity to electricity to light. It's like seeing the fundamental rules of the game the universe is playing.
And that really brings us to the most important point of all. This isn't just about motion, it's about a mindset. It proves that physics isn't just about memorizing a bunch of formulas from a textbook. It's an art. It's the art of seeing the world differently, of spotting these beautiful, hidden, predictable relationships that tie everything together. Which kind of leaves you with one big question, doesn't it? What other relationships are out there just waiting for you to find them?